Programming, big believers in strongly typed systems. If anyone wants to talk to me about that afterwards, you're welcome to. I won't be talking about it in this talk. So this talk is about uranium and airplane crashes and software. And we'll get started. By the way, feel free to interrupt. Is it okay for them to interrupt me, or should we save questions to the end? At the end? Yeah. Okay. So, just about everyone I've ever met in our business works about as hard as everybody else. Lazy people usually don't make it very far in our business or in any other business. And yet you see big differences between very successful programmers and programmers who are not successful. I don't think laziness is the problem. And I usually don't think the tools are the problem, although we are fans of tools like functional programming that help us achieve higher quality software. We all have access to the same tools, and yet you still see these big differences between people who can produce really great software and people who don't. And for much of my career, I will admit that my software has been just as average as everybody else's. But software is special. And we discovered in the early 1980s that there's a one-to-one correspondence between mathematical proofs and type structures. And we know philosophically, even if we can't always explain it practically, that any expressible software construct is mappable to a mathematical construct. Software is special. If it can be computed, you can use a modern programming language to express it. All right? So what is it that makes the big difference between highly successful people in our business and those who get normal kinds of results? And I think it's the better thinking. Right? If you can think about the problem more clearly and bring a better way of analyzing the problem and using logic to solve the problem in a better way, that's how you get to the better outcomes. It's often not the tools, it's almost never working harder, it's the better thinking. And I'm going to tell you about one of these tricks today, one way of thinking about a certain class of problem that sometimes can help you drive better outcomes. I mentioned this before, I'm a system administrator. And I'm also a programmer, and I write Haskell and C, but my first programming language was Shell. And my second one was Perl. I think, so fancy developers have a lot of advantages over humble system administrators. But system administrators have one big advantage, which is we carry the pager. All right? And so system administrators particularly care about how software fails. And one of the frustrations when you're a system administrator is when you talk to developers, it's feature, 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 feature. It's like, holy fucking shit, do you have enough features already? All right? And yet what we'll see is, adding features is something most developers can do. If you're familiar with your tools, you're familiar with the environment you're in, someone describes a feature to you and it's not impossible, you can usually add the feature. But the question is, what's the quality of the system that you're building in this way? Lots of people can add features. It's much more difficult to add features and then have the resulting system be of high quality. And we're going to see in a few minutes the relationship between those two. All right? And this is the thing I really want to encourage you fancy developers to think more about. If you reduce the failures in the system, then you increase the value of the features that you already have. And so how often is it cheaper to add value by reducing failure than it is to add value by adding new functionality? All right? Both are valid ways of adding value to the system, and yet one of them is less used. all right? It's always new feature, new feature, new feature, and yet how much engineering work do we put into reducing failure and reducing bad outcomes and improving the economics of how we reduce bad outcomes in our software? That's the thing we're going to talk about today. And it's something that I think there's not a lot of good thinking on in computer science, which is why we're going to talk about uranium and airplane crashes. 1977, this is a famous paper, and rightly so, proving the correctness of multiprocessor programs. Lampert pointed out that there is a categorical duality, a logical duality between safety and liveness. The two are complementary, and the two are logical inverses of each other, all right? Liveness is making sure that good things do happen. These are your features. Safety is ensuring that bad things don't happen. These are the things that make sysadmins angry. All right? So, we know how to do this a lot. How do we reduce the number of bad outcomes from our software system? And the fact that they are logically dual to each other suggests that the things that work, the ways of thinking about adding features, are probably not going to work very well for adding safety. All right? In fact, often you have to invert the way that you think about the problem in order to get similar effectiveness, because it's an adjunction. The two are logical duals to each other. So good things sometimes happen versus bad things never happen. Right? Those are deep logical inverses of each other. And if you approach safety with the same mindset and approach that you approach features, you're going to be very disappointed. Because to add features to a system is usually a matter of adding a few lines of code in one isolated aspect of the system. Whereas safety properties are about the behavior of the entire system. All right? You can't add safety in the way that you add features. One is an isolated property, the other is a global property. And so the first thing we need to do is start thinking differently about the nature of these two properties. One is global and negative, the other is local and positive. Lampert here gives the illustration. I just want to say, if you haven't read Leslie Lampert's papers, you are letting the best in life pass you by. He is one of the rock stars of the 1970s. I don't know why, but computer science precisely follows rock and roll. Like, 70s was amazing, and then the 80s was awful. So, like, Lampert is Led Zeppelin, and then object-oriented programming was Genesis. I mean, it was just, ooh. But Lampert was one of those great rock stars of the 70s. And this paper and time clocks and the ordering of events in a distributed system are just, they're magic stuff. Who does safety well? Not computer science. And I welcome anyone who can refer me to any computer science book that does a good job of explaining how to create safety properties in complex systems. I've never seen it. Never once. You open up a book about testing, you get a random collection of stories and informal advice. And who does care about safety? Well, nuclear engineering, the features in nuclear engineering are surprisingly simple. In fact, here's every feature in nuclear engineering. Take uranium, put it together, boil water. All right, drops mic, walks off stage. That's nuclear engineering, ladies and gentlemen. Have a nice day. All right. And yet, what do nuclear engineers spend 99% of their time doing? It's not boiling water. It's making sure that you don't kill everybody in the process. All right? Likewise, aviation. You know, you put some thrust, the Bernoulli principle, you got the lift, bada bing, bada boom, right? Aviation is easy. What's the challenge? The challenge is not having the plane smack into the side of the mountain, right? So, when you go looking for new ideas on how to create safety properties, I think these are good places to look for the thinking. And within safety engineering, there are different schools. It's an evolving field. This is the book I recommend most of all, is Engineering a Safer World by Nancy Leveson. And this is A lot of safety engineers in the more traditional school don't endorse this approach, and there's controversy over it. I don't think we need to care because we're just stealing their ideas, right? So we don't even need to have an opinion on whether this is the best way to create nuclear safety. We're just stealing their ideas to create software with better safety properties. I happen to think she's right, but it's irrelevant. So start with clear thinking. I love this diagram. All these diagrams are from her book, which is great. There are three versions of reality in the system. There's the actual external reality of your system. There's what the developer thinks the state of your system is. And then there's what your operator thinks of what it is. All right? Now, some of what I'm talking about is about operations and system administration, but I'm using that as an example of safety properties, okay? Because when the sysadmin gets called, it's a safety problem, right? Something bad has happened to the system. But these principles apply also for testing, for example. There's a deep connection, which we'll talk about later, between monitoring and testing. Anyway, the developer has an idea of how the system's working, the operator has an idea of how the system's working, and then there's the external reality of how the system is actually working. And both of these, I hope most of us have enough experience to know that both of these can be wrong, right? It's very easy for the operator to be wrong. We often aren't given any tools by the developers who can't be bothered to see what the state of the system is. And often we don't have good enough thinking to give operators the information that they need about the state of the system. It's very difficult to make an operator fully informed about what a system is doing. We'll see how to make that better. How can the developer be wrong? The developer can be wrong lots of ways about the behavior of the system. Show me a slow SQL query and a developer had an unfounded assumption about the nature of the system. All right? I assumed there were going to be 10 rows here. There are actually 4 million, and that's why your report takes 9 hours to run, right? I mean, there are lots of ways for both people, we're humans, right, to have bad assumptions about the behavior of the system. It's also possible for the system to evolve in interesting and unexpected ways because they're nonlinear, right? You can have nonlinear effects in the system, and cost semantics are difficult. How long does this computation take to run? How much memory will this computation take to run? These are not always obvious questions to answer. You need to guide people's understandings, both developers and operators, about the state of the system. And the way that you give developers feedback about the system state is through testing. The way you give operators feedback about the system state is through monitoring. And there's an interesting fact here that it should be helpful. Both of them are about measuring system behavior. All right? You're putting stimulus into the system and you're measuring its response. All right? How many of your testing scripts can be reused as monitoring? And how much of your testing can be used to inform the operators about what your system is doing? That's an easy win that many people can have. You often have a lot of testing around that if you found a way to let it be used in an ops context in addition to a dev context, you can help the understanding of what's happening in production. And if you have systems that fail a lot, that's a question that you should be asking. This is Levison's model. And we have dev and ops, and in this new DevOps world, we all have nice, clear thinking about what that is. And these principles apply even if dev and ops are the same people. Okay? This resolution is not very good. This is the critical part, is hazard analysis leading to design decisions. Okay? You should be thinking about bad outcomes and designing for them. And you should be giving that information to your operators. Here are the bad outcomes that we protect against, and here's how we protect against them. And you should be listening to your operators in terms of what the performance problems are in your system. All right? Performance, outages, other kinds of failures, right? What are the surprising behaviors coming out of the system that are leading to bad business outcomes? The more disciplined you are about doing this, and the more effective this is, the faster the rate of progress in terms of getting your system into a good state. This is the part we really need to talk about. And the STAMP model, it's a 3-step process. And it's really not very complicated. People are often surprised by how simple this is. It's 3 questions. Number 1, what failures matter? And in a commercial context, there's usually a pretty easy way to answer this question. What's going to cost us money? All right, in one form or another, either losing us sales or losing us existing clients, or reducing client satisfaction, or increasing our operating cost. But from a financial perspective, we have a lot of feedback on what bad outcomes are. Okay? And here's I think this is the one thing that changed my thinking most about how to create system safety. Is problems don't get solved by accident. Okay? If you don't have a list of the bad outcomes you're trying to protect against, then it's just chance. It's just randomness. It's not engineering. All right? You need a list of the bad outcomes. Now, do we have to put work into all of the bad outcomes? No, that's a financial question, whether you actually invest in reducing it. But I think this should be part of every systems documentation. What are the bad outcomes? Right? Your old timers and your managers, especially with financial exposure or business exposure, good enough job to address them. So the only dangerous part there is when you ask them that 2 hours later they're still yelling at you. All right? But making a list, like everyone should have a list. What are the bad outcomes? Lost sales, unhappy customers, higher support costs, higher operating costs. What are the bad business outcomes that come from our system? And especially a system that you already have, a system that you are already using, you should know at least some of them, right? I mean, when you run a system every day, you get a feeling for what works well and where the problems are. What are the problems? What are the bad outcomes? So that's step 1. Okay, what are the bad outcomes? For each bad outcome, what can cause it? All right. Here, let's pick a bad outcome. What's a bad outcome? You guys run software?
Churn rate.
Churn. So that's cancellations, right? What aspects of the system's behavior drive cancellations?
Frustration.
More specific.
Low availability.
System outages.
Yeah, system outages. Bad performance. Lack of features.
Lack of features, yes, but no, it's a valid point.
Untrustable information.
That's more what we're looking for. Lack of features is on the list, but we're going to ignore it because it's a liveness property, not a safety property. Okay? It's a valid answer, but it's out of scope. What was the other one?
Untrustable information, like they don't trust the data we present.
Can we call it wrong so that it's a technical problem? Because trustworthiness is a human problem. If it's right but they don't trust it, that's not really a technical issue. So we'll say wrong, okay?
Does that include misinformation?
Incompleteness is a form of wrongness, yeah. Wrong or missing information. Okay. Which one of these should we do? Anyone have the what?
The first one.
Outages, sure. What causes outages?
A lot of
It's not actually that long of a list.
some bad low code software can cause outage. Like if you run a bad query, you can just put the system down.
So crashes.
Creation changes.
High
Long-running computations.
Yeah. High load on the servers.
Unexpected volume.
Sorry?
Unexpected volume, like have a high volume.
Insufficient capacity. Can we say that?
Yeah, yeah.
Hardware malfunctions.
Yep.
External failure.
Except for the
Third-party
You
services.
have some outside system that's out. Lack of
Also, human error. You know, bad configuration change or something.
Do I give you the human error speech or not? All right, you've done it now. See, here's the thing about human error. Does everyone know the movie Airplane? It's rated the funniest movie of all time. Airplane, all right? Like, Shirley, you must be joking. I'm not, and don't call me Shirley, right? All right? So in the 1970s, in an airplane, like we've seen this in the movies of what those airplanes were like. Okay, there were the two pilots in the front and the navigator in the back, right? And they had the stick, and then they had the switches here, and they had the dials there, and they had the switches here, and they had the switches here, and they had the switches here, and then like on the co-pilot side, they had the switches along the side, and then at the navigator station, they had all of the switches, all right? And then like a bank of navigation dials up on the ceiling. Like I almost started putting them on the floor, all right, in the 1970s. And what happened in the middle of the 1970s is human factors psychology figured out how to measure cognitive load in humans. And it is a surprisingly stable phenomenon. All right? Humans with full mental engagement can track between 5 and 7 dynamic factors at a time. And UX now makes a lot of people aware of this. Right? This is very common thinking now, but in the 1970s it was new. So the psychologists figured this out, and then someone went into a cockpit and started counting the number of stimuli that the pilots were being subjected to. And their immediate reaction was, oh my God, I'm never getting on an airplane ever again. All right? They were death traps. Absolute death machines. All right? And if you look at an airplane manufactured in the last 5 years, what do they look like? There's the stick and there's the screen. And the screen is blue. And it has an attitude indicator. And that's it. Like that is it. And there's a big autopilot button, all right? And then there's some like, in case of emergency, do these things over here. And the amount of stimulus that a pilot is subjected to in a modern airplane is like a tiny fraction of what it was in the 1970s. And when airplane crashes happened in the 1970s, do you know what they called it? They called it operator error. If only these pilots weren't so stupid, right? I mean, we gave them the 4,000-page manual that explained what the 700 dials are, and when the 6 alarms went off at once and they had 45 seconds to make a decision, if they'd just remembered what was on page 1429, then the plane wouldn't have crashed into the mountain. Our work here is done. The problem was operator error. All right? So, when you say operator error causes outages, to go back to that whole war between sysadmins and developers, on behalf of sysadmins everywhere, I'd like to say, can you give me a break? All right? Is it really a matter of sysadmins having a well-designed operational formula and clear input that drives good decision-making with safe tools, and then the sysadmin is drunk? Is that really where failures come from? You know, that your operator, drunkenness is really the only one I can explain, because other than drunkenness or extreme being tired, being extremely tired, right? Other than that, human factors are pretty stable. And people make mistakes in their work at a pretty constant rate that psychologists can measure, and there's a big literature on it. And even if people make mistakes, the psychological literature tells you they're going to make mistakes. And the psychological literature tells you the rate at which they're going to make mistakes. And if you design the system so that it's not safe to be operated by normal humans, or even worse, if you design the system without thinking very much about how it's supposed to be operated, then leave aside the fact that operator error is not fair. All right? My problem with the word operator error is it's a bad engineering judgment. That's not actually why the failure happens. The reason why the failure happens is that operators have a model of what the state of the system is. And it's the designer's job to give the operator the right stimulus so that the operator is making good judgments about what the actual state of the system is. And most of the time, the modern safety literature says that's usually where the problem is. It's not actually that your operator is drunk or fatigued. Okay? So operator error happens sometimes. What we call operator error is a major source of problems. But I think it's a better engineering judgment to think about those more as design failures than as operator errors. Okay? And this is a big part of the challenge that I'm putting in front of you as programmers. How do we think about the ways that systems fail such that the better thinking reduces the failure? Okay? That's the operator error speech. Sorry you stumbled into it. What failures matter? For each failure, what can cause it? System outages, things that can cause it. High load, long-running computations. Now, we're not going to go, you can chase this chain and break it down further, okay? But it doesn't go very far. We're already pretty far. We've got some specific problems here, and with some pretty well-known kinds of remedies for them, right? So high load, well, you can just be operationally measuring your load and making sure you have enough capacity on a disciplined monthly basis as a matter of operational discipline. Okay, what does it take to do that? Well, you make it one of your monthly to-do items. Put it in the manual, hand it to your operator, say do this every month. Okay, well that's gonna mostly deal with your load problem, all right? And yet, how many of us have ever worked in systems where that didn't happen? Who has worked on a system at some point in their career that didn't look at load? Anyone? I don't believe you guys for a second. Right? I mean, this happens all the time. all the time. People just don't even look. And why? Because it's not on the list, right? We don't think about it. We don't have the way of thinking about it such that we have this list. All right? And that's what this formula is. This is a formula for creating these lists. And once you have these lists are usually composed of straightforward engineering challenges. All right? And the question of whether you do the work to address a given risk, that's just a financial question. You know, this thing's going to take 40 man-hours. It's going to have this business impact. Is it worth it or isn't it? And if it's not worth it, you don't do it. Okay? But you have a list. You have a list, and it's not a mystery. All right? You're not in the dark wondering where the failures lie. Instead, you turn on the lights, and you can see what these things are. And this is the big insight from STAMP, right? Hazard analysis leading to design decisions. And then you learn from your experience and you do it again. All right? And your first version will be okay. And in your next release, you take your big pile of operating reports of where the failures are, and you go back and you say, I wish I had another color pen. Oh, we missed one here, and we missed one here. Let's add them to the list. All right? And what you'll see is a rapid initial improvement in system safety leading to a mature state. Now, some systems get here like that. All right? And some systems never get there. All right? And I've worked on plenty of these, and I'm sad to say I've actually made one or two of these earlier in my career. But the fact that, I mean, we spent, what, 5 minutes on this and got to a pretty detailed list. All right? A list that you can show your operators. Here are the bad business outcomes that we designed for, and here are the specific causes, and here are our recommendations of things that you can do to address the causes. Now, does this get you to 100%? No. All right? I mean, you can still miss things this way. But you might be surprised by how far this can take you, right? It gets you up here pretty fast, right? And all of this is profit. All right? All of these failures can be avoided with better engineering, all right? By using this formula from the people who kill people when their systems fail, who've put a lot of thinking into how to avoid it. Because system complexity affects all forms of engineering, but it affects us worst of all, because no one builds as much complexity as we do, right? And yet, managing the complexity is where safety comes from in aviation and nuclear. They have a lot of respect for their complexity, right? And the nice thing about this is you're analyzing total system behavior. You're not looking at adding one change here or there. You're asking the question, for the whole system, what leads to outages? High load. Well, that's, again, a global property. And if you can come up with a global solution, then it's much cheaper than adding 100 individual solutions scattered around your system, right? Which is why the categorical difference between adding features and adding safety is important. Is when you're adding a feature, you can add it in one tiny little part of the system and ignore all the rest. When you're adding safety, you need to manage whole system behavior. And your answer from an engineering perspective needs to be about the entire system behavior. Okay? So, go over this one more time, because this is the magic formula. This is a thing that you can do in your teams today. What are the bad business outcomes? For each bad outcome, what can cause it in our system? And for each of those technical causes, how can we address it? And often the solution is simple. Often the solution is some simple monitoring, or you can make a design change that makes the failure impossible. Those are the best ones, right? And the reason why we don't do those things as engineers is we can never get to the point of having a complete list of all the problems we need to solve. I mean, how many times have you had a bad production incident where afterwards you're sitting around over beers and you went, if only we had thought of it. It would have been so easy to fix, right? So easy to fix if only we had had the idea. If only we had thought about that mode of failure, all right? And this formula is a way to avoid that regret, all right? You've got clear thinking, you've got total coverage. You might have a few holes, but not that many, and over time you're going to close them, okay? And you've written it down. In 6 months you can still remember what the analysis was. You can go back and look for the holes. You can have an engineering discussion over time about how to increase your system safety. That's what these 3 steps give you. A finite list of hazards that you've handled. It can be in your documentation. Your operators can read it and understand. People can ask you the question, hey, I think you have a failure mode that you haven't thought about. And you can have a disciplined discussion about it because they see your list. It's not a mystery what the safety properties are because you wrote it down, right? We just talked about a lot of this. The higher you can go on this graph, the more effective and the cheaper the solution is, right? So if you can eliminate the danger altogether through a design change, then the ongoing cost of that failure is precisely 0, okay? Hazard control is an example of a quick and dirty solution, like add monitoring, and if something goes badly, the operator should respond. That's a very typical kind of response to a failure case in a system. One thing I will point out to you is that the difference between those is capital expenditure versus operating expenditure. There's a one-time investment versus an ongoing expense. This is actually not a technology question. This is a finance question. This is a question about the cost of capital to your company and the expected lifespan of the capital expenditure and the depreciation schedule of the expenditure. This is a financial question, all right? And oftentimes people they mistake this financial question for a technical question, and people will argue that the one approach or the other is technically superior. But of course the answer is, what's your cost of capital? Okay. Now, if you don't know what that means, then you're probably with 90% of all technologists on the planet who, in engineering school, I don't know why they don't teach us finance, but your friendly neighborhood accountant can explain it to you, all right? Or it's on the internet, but it's a financial question, all right? And it should be approached as a financial question. And which ones of these problems are worth the investment to solve is also a financial question. All right? But the engineers can show the way. The engineers can make the list. And then for each item on the list, you make the financial determination of do we solve it and how do we solve it. All right? So these are capital expensive and operating expenditure cheap. These are capital cheap and operating expense expensive. Okay, so in a low interest rate environment, you'll do more of these. In a high interest rate environment, you'll do more of these. This is an example of an analysis at a chemical plant. And And I'm not going to spend too much time on it, but I just wanted to show you failures and inadequate controls. That's hard to read. Water getting into tanks, gauges that are missing or not working, emergency relief systems that don't work, jammed valves, pressure relief valves that are too small. Okay, we have programming equivalents of these things, right? Technical failure modes that drive bad business outcomes. So it's not an exact match, but the reason I think we should look at chemical and nuclear and aviation is because they spend a lot of time talking about failure, where in the computer science literature we don't, right? Safety is a really happy story in engineering because we've been getting increasingly good at it. The Americans do better than the Russians at nuclear submarine safety, but the US Navy put in a safety program in the mid-1960s, and they haven't lost a submarine since. Okay, and it's a fascinating read if you want to go and look at how they did that from an engineering perspective. Civil aviation, that cockpit change of the number of inputs that we expose the pilots to, literally hundreds of thousands of people are alive today who would be dead if we hadn't made that change. Hundreds of thousands of people, right? Automobiles, a very similar story. Every year we're making incremental improvements in safety of automobiles. Nuclear plants were actually always pretty safe, but they've been getting safer. When it comes to engineering in general, we do a pretty good job with safety. And I think that's a very hopeful, positive message for us in computing, because it means that it's possible for us to do better. All right? The fact that they can do it suggests that we can do it too. And if we pay a little more attention to these things that they do, all right, we can probably take a lesson or two from them. Other kinds of engineering are good at safety, and we can be too. And that's it. Questions?
So first I'm going to